Now we come to the next part of the chapter or next chapter itself, which is called as regression diagnostics. Very, very interesting chapter. Regression diagnostics. Diagnostics. Now, till now, there are many properties that we have followed or assumptions that we have followed while we were creating linear regression. Okay, if I have an equation like this, let me remove E, it might just confuse you, is equal to Y. If I have an equation like this, one of the assumption was that all the error terms that I'm getting for any kind of equation is going to be constant. Or if I take a sum of these, they are going to be equal. Or if I take a sum of the error square, then that's going to be constantly moving around the mean. Constantly moving around the mean. And we call this property as homogeneity, not homogeneous, homoskedasticity. Homoskedasticity. Skedasticity. This was one assumption that we have taken. We have also taken an assumption that these items should be unique. Like x1 and x2 should not be correlated with one another. This property is called as multicollinearity. Multicollinearity. But if we look at the real world, everything is related. Like if you talk about the bank's profitability and then we say it's independent, is it? No, it depends. It depends on what? It depends on the central policies which are designed by the center. It depends on the RBI policies which are designed by the RBI. So every bank, for that matter, is getting impacted when RBI is raising its CRR or SLR or whatever. So every bank is getting impacted when MCLR is being replaced by any other method, right? Every bank's profitability is being impacted. So in the real sense, we can't say everything is IID, independent and identically redistributed. There is certain level of correlation that exists. So every bank, every RBI policy which is changing on the interest rate is impacted because of inflation. Certain factors are common amongst them. So if I talk about macroeconomic factors in real life, they are kind of interconnected. So then we can't truly say that multicollinearity does not exist, though we want it, but there are certain ways we should accommodate for it. This is also the reality. We don't live in an ideal world where we can say that multicollinearity does not exist. Multicollinearity does exist. Okay, clear? All right. So this particular reading, focuses on fixing some of the things or dropping some of the assumptions which were kept as a standard assumption till this time, till linear regression with single variable or single, regressor or multiple regressor. Now we are going to drop those assumptions and then come up with more meaningful analysis. Okay, but before we can do that, there is also a point that I made earlier, you know, wherein we said that any kind of data, any kind of regression is good enough if it is relevant for that period. For example, if we talk about the journey for anything, let's say car sales, but during lockdown, not even a single car was sold in India for I think 2 months. For 2 months, not even a single car was sold. If I look at that as a norm, and if I take a 6-year data, this particular period of 2 months will still be present there where not even a single car was sold. And it is kind of abnormal situation. It's a kind of an abnormal situation that as a country as big as India, there not even a single car was sold. But this was a lockdown period. So on an extreme end, this was a kind of an outlier. So having said that, we need to push the outliers out before we can do any kind of regression, which we don't do it in real life, like as something for the MBA projects or something. We don't even look at identify outliers. But with the real life data, if you look at that, 2008 event, COVID event, war event, these are outlier events. They're not normal. They're not supposed to be a seasonality effect that every 3 years there would be a COVID or every 5 years there would be a COVID. These are abnormal situations that have to happen once in a lifetime. Yeah. So one good starting point for any regression is, that you have to check whether you have an outlier and test for those outlier, and then remove it if required. Remove it if required. Remove it if required. And this can be achieved through Cook's measure. This test relevant for identifying the outlier is called as a Cook's measure. Okay. Now, Let me, and what is the use case of it? Because, when I first studied about this concept, I was kind of taken aback as to why do we need an outlier. But then I understood the use case of it. Let's say I have a series which is 1, 2, 3, 4, 5, and then 1000. Can I call this 1000 as an outlier? Very easily I can say that. But if I have 1, 2, 3, 4, 5, and then I have 12 as a value, can I call this as equally confidently that this is an outlier value? Maybe not. Maybe not, because 1, 2, 3, 4, 5 are very, very tightly, closely knit. But 12 is not as close. Though it is not as far as 1000 value also, it is closer. But is this really an outlier? Should I not consider this event? Is something that I don't know. That's where it becomes more intuitive as to how do we fix an outlier? How do we understand whether this event is an outlier or not? For that, as a starting point, and that's where Cook's measure is used to confirm. It is used to confirm suspected outlier is indeed an outlier or not. Is indeed outlier or not. So in this case, by looking at it, I can certainly suspect this value 12. And I believe it should be an outlier, but I'm not too sure because 1, 2, 3, 4, 5, if I look at that way, 12 is not too far as well. Maybe it shouldn't be considered an outlier. Maybe it is an outlier. I don't know. So how should I check? I have a suspected outlier in mind, but at the same time, I want to check whether this suspected outlier is indeed an outlier. And if it is indeed an outlier, I need to remove it from my data set. I need to delete that row around this particular value and then run regression with the rest of the data. So do you understand the use case of it now? Iti? Okay.
Yes, yes.
All right. So now Cook's measure goes like this. Y hat minus J minus Y hat square with J being included, K times S square. Okay. Okay. So now what is happening is this formula is for something called as Cook's measure, which we refer to as a value dj. Okay, so what it says is you find out the value of y. You find out the value of the y with the actual model, Having said that, if my value is like a plus bx1 plus c dx2 plus e x3, sorry, c d, and whatever. Let's take this as one model. And I believe this value is an outlier. I believe this value is an outlier. So first run your regression, sorry, run your regression and find out the predicted value of y when you have all items included. And for the rest of it, use a second equation without it. Drop this item and run a second equation without this particular item, which is minus j, and then find out the predicted value. Now take out take out the difference. Take out the difference of these two values, predicted values for different years. Take a square of it and divide it by k times number of variables multiplied by which is s square, which is the sum of residuals that you have got from all items included. This model. Okay, so you want to see basically in a very, very layman language, what you want to see is if I drop a particular item in my equation, what happens to my errors? What happens to my errors? Is it increasing, decreasing, or what happens? Okay, now let me assure you this. When you drop one variable in an equation, these variables also go for a change in real life. These are not going to look like A, B, C, D. Maybe they'll look like F and G. Okay, does that make sense? Okay, Now let me try to explain this to you in another language, another way. Let's say we have a loan data, okay? And the loan data is coming out is dependent on three factors, let's say, dependent on three factors. And let's say this is credibility, credit score, maybe collateral which is offered against the loan. And let's say the third item is cash flow of a business. And you're giving like a business loan, cash flow of a business. So these are the three items on which, the loan to be given or not to be given by your bank is basically resting. Now, in this case, I would say that there is a slope. Since this comes with a slope item, like the decision to give out a loan is given as B, C, and D. And these, these items are what? X1, X2, X3. So this is how your equation looks like: A plus B times credit score, C times collateral, D times cash flow of the business. Okay. Now, if I say I believe cash flow of the business is somehow an outlier, and I drop this item and rerun the equation, rerun regression. Now, this time around, what will I have? I'll have data for collateral and credit score. I'll have data for collateral and credit score. So my Y might appear to be A plus F times X1 and G times X2. Because now if I dropped one equation, the slope, let's say earlier was 0.5, it might just come up to 1.2. If it was earlier 0.75, it might just change by, let's say, 0.2. So my point here is when you change, like even with the same data, if you're taking 10 different multiples, then you have a different slope. If you drop a few variables and run the regression on the same equation, that is where your slope will definitely be different. Make sense, Shelja? Shelja, any doubts? Okay, just to reiterate my point, let's take if I have really like a good, uh, data source, let me see. Hmm, I don't actually. Let's say I have these three as a data source: credit score, collateral, and cash flow. These three are three variables. My original equation with these three variables, let's say, turns out to be this, that y is equal to 0.5, 0.75 times x1, 1.2 times x2, and 3 times x3. This is the equation which I'm getting when I run it on three different variables. But then I believe that this dx3, d is insignificant, and let me just drop it. And then I rerun the regression on these two data points. So now my equation might get changed to x2 plus, sorry, y is equal to, let's say, 0.5 plus 1.2 x1 plus, let's say, 2.5 x2. This is what I'm saying. The slopes are now going to be different. Even if I've kept the same variable, x1 and x2 are still being retained. The slope therein, the slope that was associated with it, the slope that was associated with this value x1 is now going for a change because I've dropped the third item to which some of the weight was allocated. Makes sense now? So every time you run a regression, your slope is going for a change. Even if you keep these x1, x2 series the same, the data for collateral and credit score, the series that you have in mind, are you still the same? Yet you are going to see a different slopes associated with it. Okay. So now in this case, we are trying to confirm after we drop it and after we run it and after we run it with the suspected number, this is what we are going to get. So what is that we are trying to check with the Cook's measure? That what happens to our DJ if this DJ or the Cook's measure, if the Cook's measure is greater than 1, DJ is turns out to be greater than 1, then we believe suspected number which was dropped, suspected number which was dropped while you were rerunning it was indeed an outlier, was indeed outlier. Having said that, if dj is going to be lesser than 1, suspected number was not an outlier. Outlier. Does that make sense? This is discussed towards the end part of the book, but this should actually be the first part of any regression model that you want to check whether, here it is, Cook's measure. This should actually be the first part of any model that you want to check whether your DJ has any kind of suspected value. If you find out that this value seems off, if this you believe that this value seems off, okay, this is S square rather. This is S square. Okay, this is noted as S square. If the larger values exist, then of course we can believe that the value which we were suspecting, in this case the value was 12, which we are suspecting to be an outlier is indeed an outlier. Remove this row, take the rest of the data and then run the regression. Okay, but the starting point is you should have a suspected outlier which you are trying to confirm. Yeah. Yeah, guys. Okay. Now we discuss on the concept of multicollinearity. What is a multicollinearity? Sorry. Let's first discuss on heteroscedasticity. That's how the chapter begins. First with heteroscedasticity, and then we'll be talking about multicollinearity, heteroscedasticity. So there is a simple assumption behind any regression, which is called as homoscedasticity, which says when I take the variance of these error terms, or if I try to plot these error terms, they're going to be constantly spread around the mean. This is the mean, that is where they're going to be constantly spread around. And that is where we said if you take a sum total of all the error terms, that is where it should sum up to zero. Sum up to zero. This is what the assumption is, one of the strongest assumption that we are making behind these models. Okay, but in real life, we come across something else. Now, in real life, we might come across scenarios which look like this, where the values are, or the error values are basically increasing, or they're kind of shrinking. What does it mean? If the value of X increases, the value of Y is increasing, which means, and these are error terms here. I'm talking about error terms. So this has error terms here. This has error terms on the Y axis. It does not have Y on the Y axis. Please remember it. When I'm plotting it this way, it's not that I'm taking for homoscedasticity, checking on this one, I have E on the Y axis. I'm not having Y on the Y axis. I'm having E on the Y axis and X on the X axis here in these charts. So if I can simply say if X increases, then I can estimate Y, I can estimate error because error is also going up. X goes up, error goes up. Similarly, in this case, I can also predict if X is increasing, error is decreasing. I can say X goes up, error is decreasing. So that means there is some kind of a pattern there. The pattern exists and I've missed on the pattern. There's some kind of a pattern here. We want ideally that error value to be completely ad hoc, completely ad hoc. It should be non-forecastable. Let me call it this way. It should be completely random. It should be non-forecastable. But by looking at this kind of pattern, when things are not constantly spread out, if I look at this, if I can say simply by increasing X, I'm finding out more values of error. I'm seeing that error values are increasing. Similarly, by increasing X, I'm seeing that the value of the error terms are actually combining. All of this can be a problem. This is another case, which we call this as conditional heterogeneity. Skedasticity. Okay. And there is another third case for it, which is called as unconditional heteroskedasticity. So even if they are not spread out, even if they are not spread out, but they are completely random. They are completely random. You can't say if X is increasing, Y is increasing, or the error terms are increasing or decreasing. This is called as unconditional heteroskedasticity. Unconditional heteroskedasticity. Heteroskedasticity. Okay. So let me put it this way. Homoskedasticity, or rather, I should just change it here a little bit. Assumptions can be around homoskedasticity, or it could be around heteroskedasticity. Heteroskedasticity. Heteroskedasticity can be of two types: conditional, which can be neither of these forms, or unconditional, which is this one. Now, conditional heteroskedasticity means there are patterns that we are not able to observe or not able to include in our mainstream model itself as of now. DX3. As of now, I've not been able to include the hidden items there. There is some pattern, but we have not captured that. That is where conditional heteroskedasticity is a problem. Things where are completely random, this is not a problem. So this is a problem area. This is no problem area, no problem. So no problem means I don't have any problem living with it. If I have this kind of a model, I can use assumptions. But if I have this kind of a area, if I have some kind of conditional heteroskedasticity present in my model, that means I cannot use it. I need to fix it. This is the problem area and I need to fix it. Need to fix it before I can use the regressions there. Okay. So this is about heteroskedasticity and homoskedasticity. How are they different? Now, why do I need to fix it? Because it causes some problem. Let's understand what are the problems it causes or problems like effects or whatever you want to call it. You know, what does it lead to? Like effect is the right word. Effect of conditional. Unconditional is not a problem. Conditional heteroskedasticity is a problem. Heteroskedasticity. Unconditional is not a problem. Problem is conditional heteroskedasticity. So why is it a problem? Why should we fix it? Why do we call it as a problem? Because there is some pattern which hasn't been captured, right? That means it is coming up with the error terms. That means my error terms are not right. If my error terms are not right, that means the standard error which is associated is wide. Standard error could be brought down. If I say my standard error can be brought down, any hypothesis that I've conducted, that I've conducted, which is using this data in the denominator for calculating the score, is also not right. If this is not right, this is not right. Denominator is not right. Denominator is not right. My score, T or Z score, is calculated wrong. If I am matching those wrong values to find out what is the rejection area or acceptance area, that also becomes wrong. Clear? So the point here is if your heteroskedasticity does not exist, if a conditional heteroskedasticity does not exist, it leads to unreliable standard error. Unreliable standard errors are being produced. Unreliable standard errors are being produced because you're not completely talking about the good variance here. Okay, if this is a problem, then this same value, standard error, is used as a denominator for hypothesis T score and Z score, which is again wrong. And this is wrong, hypothesis is wrong. Hypothesis is wrong is that means you can be including statistically insignificant things which have no relevance. And that is how it leads to a massive, I would say, impact in terms of getting you to a wrong conclusion or making you add something in the model which is not actually relevant. Okay. Yeah. Clear, Giti?
Yes, yes.
Okay. So how do we fix it? How do we fix it? The problem starts. Let me use a broader pen at least. Okay. Fix. The problem starts because of the standard error, right? Because I'm using the standard error, which looks like this. Now, there is this gentleman whose name is White. He created his own version of the standard error, which we refer to as White standard error. He says if you focus, if you see there is a problem of conditional heteroscedasticity present in your data, don't use the simple standard error. Start using White standard error. Don't use the normal standard error. Shelja, you have a question?
I, yeah, I'm not able to view the presentation.
Is it?
Mm. Yes, my internet connection it is not working, so I logged in again. And now
I'll
I'm
just
not able.
do that once again. Can you view it now?
Yeah, now it is fine.
Okay. Yeah. So we were talking about how do we fix it. I know there is a problem that, and the problem is coming because everything is impacting standard error here. Standard error is wrong. That means our hypothesis is wrong. So let's fix the standard error. Our normal way of standard error is standard deviation by root n. But the gentleman named White came up with his own method of calculating standard error. He says, use my standard error if you believe your data has a problem of conditional heteroscedasticity. So rather than using simple standard error, use White standard error, White standard error if conditional heteroscedasticity exists. Heteroscedasticity exists. Yeah. So now we understood what is the problem. Problem is heteroscedasticity. We make a strong assumption that everything is split constantly around the mean, which might not be the case. We're saying it's okay. Let's look at what happens next. Could be two scenarios, unconditional heteroscedasticity or conditional heteroscedasticity. We don't have a problem with unconditional one. We are saying it's okay. If things are not constant around the mean, but as long as they're abrupt, they are non-predictable, we are still okay with it. But things become problematic if they are predictable. And that is where conditional heteroscedasticity exists. It causes a problem because it moves around with standard error. Standard error becomes faulty. That means the hypothesis becomes faulty. That means, I'm not able to find out whether the good relevant parameter is being included. So for that, the fix is rather than using the simple standard error that we have used for till now, that is standard deviation by root n, come up with another one which is right standard error and use it as a fix. Okay, yeah. Okay, sorry. I left on that part. How do we identify it? How do we detect for this heteroscedasticity? So first is we can observe it either through the scatter plot, but there are other methods as well. How do you detect for conditional heteroscedasticity? There is, of course, a scatter plot approach that we have done. Like you can simply look at the data and then find out, if X is increasing, Y is increasing or not. But that you need to be really lucky to have that. You have the error values here and you have the X values here and things are constantly spread out and what happens to the variance. If that is observable with the naked eyes, of course, you can make that bet. Another thing which you can do is called as the chi-square test factor. Chi-square test method. Chi-square test starts. This follows a different process in its own. This follows a different process in its own. Let me write down the steps here. Okay. Let's look at this process. You'll not be expected to calculate it. Okay, neither it will be given for any kind of usage. You just need to understand the concept. Okay, so that if it is tested in a theory question, you know how to go about it. The expectation here is not that you will be given some kind of a hypothesis and you need to solve it. So just listen to it. That is enough. First what you do is you usually to come up with this expression y is equal to a plus bx, what do? You run a regression between y and x, right? To find out how the equation will be built, right? Between y and x. In this case, he says estimate the OLS and find the error values. From this equation, you want to find out the error values. Square all the error values and take a sum of it. Square all the error values and take a sum of it. So how do you square for these error terms? First, I'll come up with this equation. Let's say I come up with this equation based on the past data, y is equal to a plus bx. Then whatever the value of y is, given the value of x, I know that. And then there would be a predicted value of y. There would be a predicted value of y. So whatever that x ka data is, let's say the number here is 2 and my model says it's 3. Let's say it's 4. My model says it's going to be 8. Let's say this is 5. My model says it's going to be 9. For those values of x, let's say 1, 2, 3, whatever be it. Okay, then this term y minus y hat is an error and the square of it, which is the error square. So you need to take an error square. You need to find out the error which is coming out of the mismatch of the values between the predicted value of y and the real value of y, predicted value of y and the real value of y, and calculate their error square. Once you have done that, now run the regression between error square and x. Now run the regression. Use second regression, which is to be used between error square and explanatory variable, which is x. So now run this regression because you want to find out what? If a conditional heteroscedasticity is present, if there is something that has not been captured till now. Once you do that, calculate the R square. Sorry, it should be actually explanatory variable should be y, if I'm not wrong. Give me 1 second. Not sure if it is original explanatory variable is x or y, but I'll find it out. No worries. So you take, anyways, you're not expected to calculate for it. So once you take that regression, you will get your R square. You will get a new R square. Now use this R square. R square is what? Goodness of fit or the model fit, as you may remember, and use it to build the chi-square test. Chi-square test in this case is saying to come up with chi-square score, all you need is n, which is the number of samples multiplied by the R square, which is coming out of the data which is in step 2, which is coming out of the data which is there in step 2. And you have a degree of freedom which is k into k plus 3 by 2, which is number of independent variables. Based on that, you'll have to come up with a decision that this is accept null hypothesis or reject a null hypothesis. Accept a null hypothesis if it is in the white region, reject a null hypothesis. And how do you conclude? Reject null hypothesis, or what is the null hypothesis? Null hypothesis says no conditional heteroscedasticity. And alternative hypothesis say conditional heteroscedasticity exists or conditional heteroscedasticity is not equal to 0. Okay, so if you get in the reject null hypothesis, that means conditional heteroscedasticity is present. This means conditional heteroscedasticity is present. If you have an accept null hypothesis, that is where you say conditional heteroscedasticity is not present, use it as it is. And if you find out conditional heteroscedasticity is present, change it to white standard error. Now start using white standard error rather than a normal standard error. Okay, clear? Shailja, are you confused? Too much of things to absorb. Yeah, too much of things. Yeah, I know it. This is one of the chapter that is purely theoretical. You know, this chapter is tough. Don't expect any tough questions from it. Expect only easy questions from it. That would be my advice. This looks tough. FRM Institute is very, or GARP Institute is very shrewd. It tests you on easier topics in a difficult way and difficult topics in most easier way. Okay, so don't get intimidated by it. Just remember that there's a way to check for conditional heteroscedasticity, wherein this should be the rule. The conditional heteroscedasticity is running because you are running regression alongside e square, which is not the original regression. Original regression usually works between x and y. Here you're not using x and y के बीच का regression. Here you're using error square का regression. Error square का regression. You're then trying to find out the r square based on it, which you're using it in the chi-square mechanism to get your answer. And the answer helps you derive whether conditional heteroscedasticity is present or not. Okay. Now correcting for it is white standard error. Now the second problem is that of multicollinearity, which we have assumed does not exist. What's a multicollinearity? Multicollinearity, as we said, the two values might be related. For example, if I want to find out, let's say the cost of, or I want to create a model for buying any real estate. And I'm saying it is dependent on per square feet area plus square yard area plus location plus whatever size. No, size is done plus location plus uh, you know municipality agreements and whatever. That is going to determine the cost of a plot. Now, what are the standard things which I've taken? I've taken square feet or square yard. Ideally, I should focus on only one, which is the size. In real sense, if I take my values against a square feet or against a square yard, if I have two series for that, then the cost of plot is going to be determined by both. But are they exclusive? They are just a standard unit for the same thing. Just like I can call my centimeter square or I can call it by as meter square itself. It is just two units of pointing to the same thing. It is talking about the same area. A square feet can be converted into a square yard. And when I regress to it, both of them are talking to the cost of a plot, but they're representing the same thing. There is a one-on-one relationship amongst themselves. There's a one-on-one relationship amongst themselves. I can use a standard deviation where one square yard is equal to whatever square feet. And this is the definition. This is standard. This is fixed, right? So in a way, what is happening is I'm counting two things which are representing my area, which is bad, which is not a good modeling. I'm representing same thing twice. I should ideally keep only one of the values. Either I should express the area square feet or I should express the area square yard. And this kind of relationship where I'm saying that variable might be interconnected to one another, might be interconnected to one another. In this case, we have a one-on-one relationship where I can simply go ahead and change square yard into square feet or square feet into square yard. The definition will not change. Okay, this will not change because there is a standard definition. One square yard is equal to xy square feet, whatever it is. The unit is fixed. So we call this as multicollinearity, perfect multicollinearity, perfect multicollinearity. The two variables are basically repeated and they are exactly representing the same thing. Two variables are repeated in the regression and both of them are representing the same thing. There's a one-on-one standard relation. But there could be a case of imperfect multicollinearity also. This kind of case where we have imperfect multicollinearity linearity can exist when we have two variables which are talking almost on the same thing yet not same. For example, I can talk about this x2 to be inflation, and I can talk about this one as cost increase. So one is talking about that the inflation rate has been increased by the government. And then I'm talking about that the input cost has increased. Now, of course, that is bound to be in effect, right? If the inflation is increasing in the economy, how can you not expect the input cost of your production not to increase? So there is a relationship. Of course, there is a relationship, but the relation might not be perfect. For example, if you go to stock market, right? Every time there is a change in the stock, it is being reflected in the mutual fund, right? But if you go to a restaurant, even if the onion prices were up and down, tomato prices are going up and down, they'll not every day declare a new price for that dish. They'll not say that today's, whatever, butter paneer masala is at, 80 rupees and next day it is 120 just because the tomato puree is expensive. And the third day it is 150 and now I'm coming back to 80 rupees. That's not how things work. Even if it is high or low, restaurant will still keep the same price on the menu. In real life they are dependent, but it also depends on elasticity, they also depends on other factors. So we know that this is not a perfect relation, whereas square yard and square feet is a perfect relationship. It's a perfect relationship. This is also a relationship, but it is not perfect multicollinearity. It does not represent perfect multicollinearity, it represents something which is imperfect multicollinearity. Clear? Shailja, any questions? Okay. Again, in case of imperfect multicollinearity, that means the R square between those values should be high. That means high correlation. High correlation is a problem. Low correlation is not a problem. If things are, let's say, they have a lower correlation. Let's say, they have zero point 0.2 as a correlation or 20% correlation is not a problem. But let's say if it has a correlation of, let's say, 0.9 or something, that is where it is a problem. Multicollinearity means you're repeating things twice, almost they are the same, right? So lower correlation amongst the X factors, amongst the different factors which are used for regression is kind of taken granted. There are cases like that where we'll include both, but that's where we are expecting lower correlation between different factors being used. If the correlation is high, that is more of a problem. Low correlation is not a problem. Absolute or perfect is definitely a problem. Perfect multicollinearity means that the correlation is actually 1, is definitely a problem. Okay. So high or perfect correlation between these values is a problem. Low multicollinearity amongst the data x1 and x2 are being related is not a problem that we should fix, because we understand in real life everything is connected to macroeconomic factors in some way or another. Like if we are like if we are analyzing, let's say, car sales. So car sales is dependent on what? Personal disposable income, because the taxes are being moving. Why personal disposable income taxes are being moving? Because the government wants to make money. At the same time, if the government is giving less money in the hand of people, that's where people will be spending less. So the car sales is impacted with by another factor. So in real life, we understand there are different factors and there would be some kind of a low correlation that would exist because we are operating in the same economy. Because we are operating in the same economy. But what you really don't want is high multicollinearity. Also, in fact, this is one point which I've missed while I was doing, the chapters on regression or multi-regression with linear regression with multiple regressor. There's a point that says, if you take any data for that matter within industry, right, and compare it with any other thing, with stats, with numbers, with formulas, we are somehow going to establish some relationship, right? Even if I talk about, Joe, like, Bill Clinton or Joe Biden's presidency against, the number of matches that we are winning or losing, I can have some kind of relationship there as well. But does it have any kind of economic relationship? Does it have any sense to have that? is something that needs to be seen. So linear correlations sometimes give you relationships which are by chance, which are by chance. For example, if I say, rainfall in Africa is connected to my stock price performance of debt funds, or let's say recovery rate of Bank of Baroda. Now, whatever happens in Africa because of a rainfall, and Bank of Baroda's own credit model saying that they are basically, recovering loans well, has no correlation whatsoever. Yet with the data, we can prove that there could be some correlation. So even if that said that linear correlations sometimes might give you stronger relationships between two things, but before even you use that, you should ask yourself this question, whether it has any kind of economic significance. Now, if I talk about, you know, African rainfall against, there is this stock which is called, I think, Kasturba Industries, which grows rose in Africa. There is still some relation that this stock will perform well because Africa has received rains, but not otherwise. Economic significance, even if you have established a correlation, should be should be questioned, even if it makes sense. If it has to be making sense rationally also. If it is making rational sense, then go ahead and connect the two variables. If it doesn't make any sense, then you are leaving things to chances only. There is no economic thing. There is no rational. There is no logic to it. Let's do it things logically. Let's not do it just because we have two data sheets and they're talking to each other and the correlation is established. Maybe it is by chance. Maybe we don't have any significance there. Maybe there is no logic to it. Okay. In that case, we are saying multicollinearity. That's where it's a very important tool that two relationships or two things should be talking to one another. Now, why is it a problem? Even if it exists, why is it a problem? A, we are repeating two numbers itself. And think of it that way, it leads to something which is called as a type 2 error. Type 2 error. And how does it lead to a type 2 error? Type 2 error. Let's see, this is the pie of the data. Let's just understand it in a very, very layman language. This is one cut which is coming from your one factor or one first x1. Now you are creating another cut with the other factor and it's going to be lesser. It does not make sense to have, or rather, which is not going to move things a lot. Mm, Give me 1 second. Let me try to explain it to you again. So let's say this is your data. Let's say this is your x1. And now I can include another factor which is just incrementally adding value x2. Because things are necessarily, they are both representing the same thing. It does not make sense to include two factors when I can have only one factor, possibly capturing for both the data points. You're getting it? Maybe I can have one factor. Maybe I don't need x1, x2, x3. Maybe there is only one x1 I need. If I do that, I can get rid of x2 and x3 as well. I can just increase the slope of x1. I can just increase the slope of x1 and achieve the same results. All I want is that I form an equation which is best indicator of my y. I want to have the best prediction for y hat. In my model, whatever is coming to be the value of the y, that should be closer to reality. That is what my motivation is. So even if I'm getting different values of y, does not make any difference. Cool. So again, if multicollinearity exists, it will increase the standard error and it will lead to type 2 error. Standard error increase, that means confidence intervals are also going to be wider. And if they are wider, that leads to a type 2 error. So other case was leading to a type 1 error. The previous case that we discussed about conditional heteroscedasticity, that brings us type 1 error. This one, if present, it brings us type 2 error. Both of them impact via standard error. Okay, clear? Okay. Now the question is, how do we detect for this multicollinearity? First is we have addressed the problem. Why is it a problem? Where it impacts? Now we are going to understand how do we detect this problem, and then we'll find out the reason for it or how do we fix it. So the third thing is detecting multicollinearity. There are three approaches for detecting multicollinearity. First is a scatter plot between x2 and x3 maybe, x1 and x3 maybe, x2 and x4 maybe, whatever those values of x's are. You can simply plot them and find out whether the relationship exists. But these should be x's. There is no y here. So you can take x1 here, x2 here, you can take x3 here, x4 here, and then find out with the scatter plot whether these relationship exists between these variables themselves. The second one is basically a t-test and f-test approach. And the third approach is called as VIF, which is variance inflation factor. Variance inflation factor. Variance inflation factor. So this is very easy that you can create a scatter plot out of different x's or different independent variables in your data, and then you find out whether the correlation exists between those independent variables or not. Okay, this is easy to get. Now we can talk about the other thing, which is the F test and the T test scenario. It is very specific to case where okay. So where is this T test and F test being used? And we are going to exactly discuss on this one with an example. T test and F test approach is used where you're seeing that, let's say this equation A plus BX1 plus CX2 plus DX3, whatever. When you take a R square of this complete model, when you take an R square of this complete model, it seems high. It is completely high. R square is completely high. But if you test for each of these components, let's say I took a regression or I took a hypothesis of this one. Sorry, equal to and no, okay, B's. This becomes my null. This becomes my alt. Then I took it for C is equal to 0, C is not equal to 0. Then I checked for D is equal to 0 and D is not equal to 0. I checked for all of them. And then I found in each case that things are insignificant. They are closer to 0. Yet I'm saying if all of these things are insignificant, yet when they're combined together, this is causing the total R square value of a model to be high. That means that is where three insignificant things are bringing a massive impact. Three insignificant things are bringing a massive increase in R square. Now, how can that be? If they are insignificant, then they are insignificant, right? If they are insignificant, then combined together, how can they bring a higher R square? And this is where there is a applicability of this approach. So let's go to the book where they have given a specific example and mark this example as an important, though it's a one-liner example, but this example is really, really important. That as to how you will conclude it. So Bob Watson runs a regression of mutual fund on average PV, average PE, and average market capital based on the following results. There are three P values given, and the R square of the model is 89.6, which is quite high. 89.6 is almost closer to R square of 90, which is good, which means it is performing good. The model is really good. Now you want to find out for each individual factors. That means we have a model which looks like this. A plus 3.52 average PB plus 2.78 average PE plus 4.03 market cap. This is explaining my variable Y. This is explaining my variable Y. In fact, in this case, they have not given any coefficient, so I would remove that. Then this is explaining my variable Y here in this equation. So I would believe if the R square for this equation is really high, all these things might be significant. All these things might be significant. But when I check for that, the p-values here are quite high. The p-values here are quite high. Now, just to refresh your memory, what does the p-value high means? If a p-value is high, if a p-value is high, okay, this is 2.5 on each side, against which my regression area is, I will call that as reject null, right? But if my p-value is high, let's say it's 15%, or I can call it as 15%. If it is high, that really means 7.5% area is here and 7.5% area is here, right? That means my p-value says that I'm currently in what? Except null hypothesis region. Except null hypothesis region is where I am in. Except null hypothesis. And what does the null hypothesis says for anything? If you have a null hypothesis says that anything, like in this case, average PV is going to be insignificant. Here I'll say average PV is going to be significant. So this is insignificant. This is significant. Okay, if you look at it this way. So all of these are greater than 10%. If I were to evaluate it like 2.5% with 95% level, or even if I do that with a 90% level, then I would say 5% each tail. 5% each tail. Even with a 90% confidence level, I would mean 5% each tail, right? Here I've showcased it to you with 95% level, where 2.5 is getting split on both sides. Okay, let's look at the the explanation given here, which is very good. I mean, just please mark it down as very important from understanding point of view. The R square, the final R square for the model is high, 89.6, which means all three variables explains the models well, which suggests that three variables as a group do an excellent job of explaining the variation in the mutual fund return. However, none of the independent variable, average PV, average AE, and PE, and average PV, average PE, and market cap, none of the independent variables individually is statistically significant to a reasonable extent because the p values are greater than 10. If they are greater than 10, let's say he's evaluating it at 90%. He's evaluating the same thing at 90%. That means he expects 5% here, 5% here. But yet, even with the 5%, our data is 7.5%. Our data here is 7.5% each side. So we are still in fail to reject region. We are still in the fail to reject a region or accept null hypothesis, which still gives us the same thing, that this is insignificant. If all three are found to be insignificant, this is the classic indication of multicollinearity. This is the classic indication of multicollinearity. So what you want to see as a result, once you, like, what are the indicators to it? The indicator is when you conduct an F test or when you conduct, say, R square test, you find a good relationship amongst all the variables. But when you start checking at things individually, that is where you find out a problem. Okay, individually things might not be explaining the model well, but combined together they explain the model well. At least I would say that few of these values should be significant, but individually they are insignificant, all insignificant values, but bringing a lot of impact together. That's a classic case I can explain multicollinearity. Yeah, clear, Geeti?
Yes.
Yeah, go ahead. You were asking a question.
No, I was saying yes.
Okay. All right. The third approach is to find out the multicollinearity is variance inflation factor. Okay. So the approach start is that you want to pick up each and every individual item on this and then want to test for it. So how should you go about it? First of all, First of all, you'll run a regression with y, and let's say the equation comes like this: a plus bx1 plus cx2 plus dx3 plus ex4. So you have four variables, four independent variables which are explaining things. Now let's say you drop one of the variable x1 and then recalculate the r square out of the equation. You recalculate what would be the new equation, calculate the r square on that, and this recalculated r square is going to be represented as r square minus x1 because it excludes the x1. You're deliberately leaving that out. You know it is relevant, but you're leaving it out. Okay, then you calculate VIF, which is 1 upon 1 minus r square, which you have calculated by excluding this x1. Okay, if this answer comes out to be greater than 1, and this would come out to be greater than 1, this would come out to be greater than 1 only if your r square is going to be greater than 90. If your r square is going to be greater than 90, that is where this answer would become greater than 1. You can say multicollinearity exists, otherwise not. Otherwise not. Okay, so this way you have checked for multicollinearity of between x1 and the value y. Similarly, you'll have to check for all these values x2, x3, x4, x5. All these values you'll have to pick up one by one and test for this for its multicollinearity with the factor y or with the y data. Clear? So you need to repeat this exercise. Thankfully, this is also something that will not be tested on as far as the elaborate process goes. You might be expected to calculate 1 upon 1 minus r square VIF, that's it, and conclude whether multicollinearity exists if the answer is greater than 10 or not, but not beyond that. As I said, the tougher the concept they have, the lesser they'll test you on that, or they'll give you simpler questions on that. The simpler the concept is, the more they'll try to test you on the tougher concept or tougher questions around it. Okay, so now we have three ways. If you look at evaluate, if you evaluate, you have three ways of looking at multicollinearity. First way is the scatter plot. That means take all the variables and try to plot them against one another, x1 against x2, x2 against x3, and find out whether any kind of relationship exists between any of these items. The second one that you can have is basically a approach which is based out of f-test and t-test. Like f-test gives you a bulk test. If you know that things are significantly changing, things are significantly being explained, check each of these individual things and check whether they are significantly contributing or not. If they're not significantly contributing, but the resultant contribution is still greater, then it is multicollinearity. And the third way is you come up with the variance inflation factor, wherein you first run the regression, drop each variable, test for each variable one by one, drop that variable, create the rest of the equation, calculate r square, check for the removal of the r square by 1 upon 1 minus r square, excluding that particular thing. Check what is the impact there. If the VIF is going to be greater than 10, multicollinearity is definitely present. Okay, and multicollinearity brings you type 2 error. Multicollinearity brings you type 2 error, whereas the first concept which we have done today was about conditional heteroscedasticity that brings you type 1 error. Remember that. Okay. Now, if you have found out that multicollinearity exists, what is the way out? How do you fix for multicollinearity? How do we fix for the multicollinearity? The fix for multicollinearity is find out that regression. If your x1 and x2 are same, then deliberately leave one of the component out and then use it for regression. That's one approach. And this is handled by a system with something which is called as stepwise regression. Have you ever heard of this word, stepwise regression? Stepwise regression is very, very common. Stepwise regression. So no one has time in the real world to talk about all the variables, drop them one by one, check for it, check for all the things together individually against one another, find out whether things are working well or not. No one has that kind of time in the world. to check for each and everything and then come up with conclusion. You want to know that things, but you also want to be smart about it. So what happens in real world is we go for something which is called as a stepwise regression. So we have in real life, let's say I'm talking about Reliance as a stock and I want to predict for Reliance. So what are the factors related to Reliance? Reliance is an oil and gas stock related to Indian equity. It's a large cap. Okay, in real life, what happens is there are factors which are assigned to Reliance. There are factors which are assigned to Reliance. Now, with the stepwise regression, what happens? The equations are self-formed by the software. They will first come up with an equation B like oil and gas factor is equal to value of Y. Okay, they will test for this hypothesis. They will test for hypothesis. Is it significant or insignificant? If significant, retain it. If insignificant, delete that item. Check for the error. Error values still find out to be prominent. Go for next step. Retain oil and gas. Go for next inclusion. Take Indian equity. Now the equation will become B times oil and gas, C times Indian equity, and then come up with E mode. Then this factor will be tested, whether the contribution has led to any kind of increase in adjusted R square or not, whether it is increasing the accuracy of my model or not. R square corrected. Then we'll check for this idea, whether this is significantly contributing or not. Checked. It is significantly contributing. Whether these two have any kind of a multicollinearity existing between them. This is no, no multicollinearity found or no high multicollinearity found. Fine, retain this factor. Go to the next factor. Take up large cap. Large cap when is included? Are they having any kind of correlations with these two factors? No. Is this the new factor? Is it going to increase the R square or decrease the R square? Like adjusted R square is going to be increased or decreased. If it's going to increase the adjusted R square, is it contributing significantly to it? If all the answers for all the things is yes, retain it and add more factor. Pick up fourth more factor and include it. And that's how it works in the real life. No one has time to find out which factors are we talking about. They are self-driven by factors with all artificial intelligence and whatever you want to call it. There are set of factors which are identified. These algorithms help you find out, track any security, map them to a set of factors automatically based on regressions and the hypothesis. So that is the usual use case through which you can get rid of multicollinearity, because anytime the system finds out two things are correlated, they'll drop the one which is less relevant. They drop the ones which is less significant. They want the more significant one to be included. They want the more significant one to be included. And that's how it works in the real life. Clear? Okay. Now let's look at the other part. So basically this chapter revolves around two things. One thing is an outlier. Second is fixing the two problems of multicollinearity and heteroscedasticity, conditional heteroscedasticity to be more precise. And second is multicollinearity. Okay. Now we come to this part about model specification. Model specification, which is a very interesting topic, purely theoretical. It says model specification. How long should my equation be? Should I have an equation like this, which should be preferable, or should I have an equation like this? Let's say k times x 100. Which model should I prefer? This is more elaborative. This would need more input. Does not need input, much of an input. I just need one series of data, but which of them is a better model? Which of them is a better model? So what should be the model specification? That is where they say, go for a model, go for a model which is balanced. You don't want to include a very simple model which gives you a higher error rate, and you don't want to include too many things just to suppress your error that it leads to wrong in sample forecasting. In sample forecasting. What is an in sample forecasting or out sample forecasting? I'll talk about it. Okay. Okay, let's say for Reliance, I've taken the data from 2016 till about 2022, and then I want to comment on what would be the performance for the stock in 2023. And with the KPIM model, capital asset pricing model, which only focuses on one factor, which is market. What is the market price? What is the market sensex happening? It is entirely based on that. And that is where I can still predict the value in 2023. I can still go ahead and predict the value of Reliance in 2023. I can still do that. But the point here being in 2023, do I believe it's entirely only driven by market? Business is no credibility of its own. No Geo business is playing. No Reliance retail is playing. It has no significant oil price increase. Has no bearings on the business. It's entirely just up because the stock market is up. See, the bottom line for KPM is you are saying market is up, that is driving Reliance. Market is up, that's why Reliance is up. Is that only because market is up, Reliance is up? Reliance has no identity of its own. Think about it. Reliance has its own business. It has its own balance sheet. It has its own clear cash flows. It has its own sub segments which are performing well or not, right? But by doing KPM, what you are saying is just because Sensex is up, this should be my expected return. That's the most easiest model someone can look for. But that's not a correct model. That's not the correct model at all. That is not the ideal model. This is the base model, you can say. This is one factor, but you need to include many other factors because Reliance is driven by the oil prices. Reliance is driven by what happens to the Reliance retail business. Reliance is driven by what is happening to its deal with let's say other companies, its joint ventures it is forming, the kind of products that it is rolling out. Everything has an impact on Reliance stock price performance. It's not just up because the stock because the Sensex is up. So that is where we need to include something like that. Now, if I take this data from 2006 to 2012 and then comment on 2023, this data on which I increased or I created my model A plus BX1 is equal to Y. This is called as in-sample data. Okay. And this model where I'm using 2023's data up to 2022 to comment on 2023. This is called as outsample data. Outsample data. This is called as outsample data. So think of it. We have an in sample which is used to come up with an equation, and then I want to apply this equation. Apply this equation to the outsample data for the forecasting. I want to apply this data for the outsample data for the forecasting. Now, if my forecasts are closer to what the actual results are, I'm a good analyst. If my outsamples are not closer to what they are, that is where it is a wrong thing. Clear? Clear on the difference between in-sample data and out-sample data? Okay. Now, let's understand if I make this equation too long, if I overfit this equation, if I make this equation too long means I am overfitting. If I make this equation too long here with the in-sample data, with this black box within the in-sample data, it might not perform as well in the out-sample data. It might not give me good forecast because it is too tightly stitched to it. In order to chase my error returns or errors down, I have created such a broad equation which works very well in the in-sample data. But the moment I make it out in for an out-sample data, that's where the forecasts are nowhere closer to reality. So this leads to a problem which is called as overfitting problem. Whereas an equation which is as simple as this, which is just saying Sensex is up because, sorry, Reliance is up because Sensex is up, the KP model, is leading to something which is called as underfitting. If I use this kind of data, then I'm saying by 2022 onwards also, Reliance is only moved because Sensex is going up. It has no credibility of its own. Just because Sensex is up, it is up. So that is also leading to problems. So when we talk about in-sample data and which is used for out-sample forecasting, which is a real case, we study past data to predict on the future. So the past data itself is the in-sample data, and the future one which we are talking about is called as our out-sample data. So we are studying in-sample data for forecasting on the future. But if our equation is too long, it leads to overfitting, which might not perform. If our equation is too short, which leads to very loosely defined model, which will again not perform. And that is where we should go for something which is a balance of two, which is a balance of an overfitted or an underfitted model. Yeah. Now, again, there could be some errors. The errors that could come in because of the outsample can be of two types. There could be one error which is like this: a plus bx plus c. There could be one error wherein there is an error between these two values, and there could be one which could exist between these two values, x and 0. And there could be a value which is problem which is here. This one, the first part says the error which can happen where your error terms are conditionally heteroscedastic. You have not taken into consideration all that you could, and there are more variables that should be added. In fact, you can probably dilute this equation by looking at this, like, gx h x2, and then this type of equation, you can convert this equation into this kind of equation, so that you add more variable and your error term is becoming more and more ad hoc. You want things to be non-predictable. You want error terms to be completely ad hoc and non-predictable, or non-forecastable, to be honest. So this is one way. This is one way. The other way is, that is what the first problem is all about. The second problem is that you are capturing wrong x. You're capturing wrong x. Maybe there is some other x which you have missed. Wrong. You have included wrong x. Okay, you have included wrong x. So let me give an example for this omitted variable. We call this as an omitted variable bias. You have included wrong x. Omitted variable bias. That means there is some other factor which is also related to this one. Some other factor which is also related to this one, and you have included a wrong factor. Now an example, an excellent example I came across for this one was, uh, okay, let me think about it, how to articulate. Okay. All right. So when I was a student, there were a couple of guys whom used to study with, and they were all, sons and daughters of doctors. Okay. They used to score really well academically. They used to score really well academically. Now, if I were to take this equation, usually, during your school time, you find out a bunch of people who are very good with English language, or, very good with some particular skill set, or their personality is very, very attractive just because they have like an army background or whatever. Now, having said that, you form a common belief that people who are coming from, who are actually, and they read a lot of books actually. So if I go by the pattern, that people who have lots of books at home are the ones who are going to be successful. Who have a lots of books at home are the ones who are going to be successful. They are going to score academically. Then the librarian would be the Prime Minister of India, right? Or not Prime Minister, but the chief scientist, I can say, for ISRO at least, because he is surrounded by books all the time. Okay. So the variable that I'm considering here is that the number of books someone has in his house is going to determine the success of his academics. Whereas the other variable is about how many times is the person reading the book because he has an environment which is academically aligned. If your parents are doctors, you are forced to study somehow. You have a very padne wala environment at home. If you have that padne wala environment, you find more books there. Not, the books are not just for showpieces there. You read them. You read them. And the better you read them, better are your scores academically. So the right factor is not that you keep more books and that's where you can basically score well academically. That right factor is not there, though it is very, very significant relationship. It is a right factor which is determining if you have access to books, you will be doing good. But the right point is not saying that access to books. Right point is whether you are actually reading it or not, whether you have that environment or not. So even with that, all three factors are connected. Like, people who are doctors create an environment in their homes wherein they clearly have more books and they have academic environment there. Sons and daughters of those people read more books, and that's where they do significantly better. So just by virtue of, one day I decide that I should go to the market and buy 10 bundles of books, keep it at my house, and I'll be suddenly successful, is not the secret formula. I'm using the wrong variable there. I'm using the wrong variable there. The actual variable is the parenting. The actual variable is not the number of the books that is kept there for me to score bright. The actual variable is the parenting, that they have an environment where they're forcing their kids to study more, or read more so that they have a learning. Okay, so you should be within the, like, though two factors seem to be related, you need to choose the right factor. You need to choose the right variable. You can't use non-relevant variable, though it will still fix it, though it will still look relevant to you. Though by keeping the number of books, there would be a definition, there would be a definite relationship that would be captured, that people who have more success are having more books, or whatever, the people who have more books are having more success. But the primary determinant is not that person having more books is successful. A librarian might be the richest person of India then. The success is parenting. The success is somewhere else. You shouldn't be just surrounded by books. You should make use of the books. Okay. So that is what is called as omitted variable bias. Though the variable is connected, you have omitted it. You have not taken the right variable. You've taken the connected variable, but you're not focusing on the right variable there. Now, if you omit the variable, that is going to create a bias in your judgment. And that is what is a problem. The bias could be a positive bias or a negative bias. But bias is like wrong thing against what you expected it to be. So that could be over bias or under bias. Okay.
Okay, so yesterday we covered a lot of different aspects. Primarily, it was about two problems which were kept as a standard assumptions. We dropped them and we understood how do we deal with it, like multicollinearity and regression. Sorry, one was multicollinearity, another one was heteroscedasticity that we have dealt with. Now, when we come to this particular LOS model specifications, we learn that how underfitting and overfitting both could be a problem. Underfitting and overfitting both could be a problem. We don't want a model which is just as short as this, whereas we don't want a model which goes up till about a thousand numbers, k 1,000 or something like that, because it's going to be increasingly complex. We're going to study more about underfitting and overfitting of the model and in sample and out sample once we do the last two chapters on the machine learning. That is where it's been described much more, you know, uh, in completeness, it has been described there. But what we will cover is only the essence of it. When we talk about model specification, the one common error is about omitted variable bias. Omitted variable bias. And that's where we understand it can be in two forms. One is that you have included some other variable which was supposed to be correlated with this. And rather than choosing, the real variable, you have chosen some other variable, where I gave you the example of a doctor, and it was actually the parenting that was mattering rather than, how many books someone has collected over a period of time. The another example is if you have missed the variable entirely. So if there was something like an x2, which should have been a part of it, which is either not correlated, but it's completely missed, that is where this kind of variable should also be included. That's where omitted variable bias creeps in. The problem is when you have a bias, you should get to a balance. Sometimes you allow for a bias, and that is what we are going to study under machine learning much more in detail. That sometimes we allow for a bias because the ultimate goal of anything is if you have an in sample data if you have an in-sample data and you're using and you're coming out with an equation, the equation is meant to solve for this purpose of out-sample forecasting. Out-sample forecasting. Okay, it is done for that. If the out-sample forecasting is to be too tight and you're not able to get real good answers, then there is no point. You are okay with directionally correct answer and keep a little bit of bias if that helps. Okay, but we are going to study more of this in while we do artificial intelligence based chapters. But the point that is being focused here is if your in sample equation is not giving you out sample forecasting results, what are the strategies that you can follow? Again, we are going to study these two strategies again later with a different name or probably with a little bit amended name, but let's go through them. For now, one is called as generic to specific model. Generic to specific model. Okay, which is nothing but how machines basically do backward step regression. There's something called as a backward step regression, which is not explained in the book, but let me tell you something about it. So yesterday itself, I talked about step regression, which was a forward step regression, wherein there were certain factors which were assigned to uh, a particular stock of Reliance, and that's where the equation was elongated. Like every time a new factor is included, its hypothesis is being checked, its consistency with other multicollinearity with other variables is being checked, its F test is being conducted, and after that it's found to be satisfactory. That's where a new variable is being added. Similarly, the other way for that is a backward step regression, wherein let's assume you are added a lot of factors in advance. You're getting exposed to hundreds of factors, and you have an equation, let's say, containing 100 x's or independent variables. And after that, the computer itself tests for F regression, F test, and T test, and then tries to eliminate eliminate the independent variables which is not meaningful for this equation, and then kind of reduces and condense this equation from a bigger, like 1,000 steps, 1,000 independent variables, to only a handful of variables which are meaningful to explain things. And that is what is called as backward step regression. The same concept is applied here and has been termed here as generic to specific. It says starts with a bigger thing, keep the macroeconomic factors, also keep the generic factors specific to that industry also. And with all these factors, of course, you'll have a very long equation. When you have a very long equation, allow the system to screen that out or eliminate the factors which are not contributing well. And then by eliminating those irrelevant factors which are insignificant, you condense your equation into 4 or 5 meaningful variables. And that's how you get a variable, or an equation which is of an optimum size, which is not too long and is also not too short as well. Preferably, the industry standard is not to exceed, even with the worst of the model, keep 3, 4, but not to exceed 10 variables by any chance. You know, you should, with everything, you should have maximum of 10 variables, maximum of 10 variables. Minimum could be 2 or 3. Okay. The next strategy they have told about, how can we improve within sample data about the outsample forecasting is, if we have m-fold cross validation. M-fold cross validation. Okay, it says when you have the whole historic data, if this is the historic data, okay, take this much data for preparing your equation. Take this much data to test your equation. Test your equation, whether your equation is working fine or not, whether the results that you're finding are good or not. And then basis that, then use it for forecasting. Okay, usually what we do is, or what a layman person without this background will do is, he will take the whole of the data as a historic data, come up with the equation and start doing the forecasting. These guys say, take, like, leave a small portion of the data, leave the small portion of the data just for testing. You come up with your equation based on majority of the data that you study, leave a smaller section of that data just to test it. And once you find it satisfactorily estimating for the items, then use it for forecasting. Okay. Okay. Now, these are the two things which have been mentioned, but we'll study them in detail. So I would say, even if you want to skip it right now, it's okay. This particular topic, because this is just an introduction that I've tried to do it here. But honestly, much more advanced version will be done in those chapters, which we are not very far off from. Then we have residual plots. Now, how do we get to the residual plots? It says whenever you have residual is what? Errors. And we want to plot those errors plotted. How can we plot those errors? How can we plot those errors? There are two ways in which we can plot those errors. Okay, give me 1 second. Is something called as the standardized version. The standardized version says that you should keep your errors divided by the standard deviation of these errors on the y-axis, and then you have the projected value of or the estimated value of y on the x-axis, and then look for all the errors should actually fall below 4 standard deviation. Anything which is above 4 standard deviation is concerning. Anything which is above 4 standard deviation, think of it like a tolerance limit. Think of it like a tolerance limit. On the on the x-axis, you are taking the predicted value of y, and on the y-axis, you are taking the error value which is standardized. We call it as standardized error value which is divided by the standard deviation, and you want to keep it below 4 standard deviation. Anything which is over it needs analysis. Like this is like either this item shouldn't be there or it needs to be adjusted or dissolved somewhere. Like what's the case when you have very high value? That means you have probably it as an outlier. So go for Cook's measure and try to dissolve it, try to remove it out of the chart. That's the first way. The second way that you can plot it is if you have error squares reflected on the y-axis and you have the predicted value of y reflected on the x-axis, and then you plot them. Then you plot them. Clear? Clear? Okay. It also says about best linear unbiased estimator. Best linear unbiased estimator. Now, what is best linear unbiased estimator? We have already talked about that, which is a title given to something which is fulfilling most of the properties. And in our previous topic, we said mean is the best linear unbiased estimator. Now, what is for the similar thing for OLS? Also, we are talking about best linear by unbiased estimator. The assumption that is there is needs to be satisfied to create best linear unbiased estimator. First of all, we understand the relationship should be linear. The residual should be homoscedastic, which means an ideal situation that they are constantly spread out above and below the mean. Independent and have the expected value of 0, IID. All the series should be IID. And the last assumption is if there are no outliers, that means there are no outliers. Perfect, perfect linear, perfect correlation, and all the points are on the line. If there are no outliers in the data, sorry, if there are no outliers and the residuals have an expected value of 0, residuals have an expected value of residuals is basically equal to 0, we can relax the assumption of normality of residual distribution. Now, why is it relevant? Because when we did the assumptions, one of the property we took is that if you plot all the error values on this axis, you should expect a normal distribution. You should expect a normal distribution. That is where this property is important. If there are no outliers, if the data does not have any outlier data, which means Cook measure has basically removed all the outliers and the residuals have an expected value of 0, we can relax on the assumption of normality. It can be tested in theory, not with any kind of numerical, but it can be tested with theory. Clear? Okay. Now allow me a couple of minutes. I'll show you something which is going to summarize probably our last 2 to 3 chapters. Okay. And this is only like for your own understanding. This is nothing to do with exam. Okay. All right. So let me try to summarize what we have studied in last 2 3 chapters via a real example. And this example, not real example, but I've tried to simulate it for you. Let's say we have X and Y. We have two series X and Y, and we definitely see that as the value of X is increasing, the value of Y is also increasing. So we definitely understand that the relationship between X and Y is positively related. Now I want to find out, and do some linear regression out of it. How can we create a lot of things out of it? So first of all, let me take this data and then I will run a regression. How do we run a regression? You go to data, analysis, and uh, click on this option. Let me try to do it once again. Okay, first of all, let's come to this point. When we take X and Y and we try to plot it, there is this points which are captured, and if you click on the trend line, you will get a linear equation. So this is the linear equation which we have. where this is the intercept and this is 4.94 is the slope for the data. As you can see, all the points are not lying here. And once we use this equation 4.94 plus 1.89, we get our estimates with the same values 88.9, 88 minus 88.9 plus 4.94 multiplied by the value of the x here. We are trying to get the estimates, which are of course not matching. So 64.2 is not 100, and this is what we call it as an error. So once we have to take an error square, we take square of minus 35.8 is what is, this is e square, this is e, this is y, this is the estimated value, this is the predicted value of y. Okay, as you can see, linear regression, all the points never crosses this. Okay, now let me go to that data where I can talk about regression. Data analysis, data analysis, regression. Let me put a value C3 to C7. Y is, okay. Now I'm going to take some things here. Let's say I'm going to want that data to be represented here. Worksheet produced by residuals, standardized residuals. So look at the residuals. The one that we have discussed where we want to keep it below 4 standard deviation is standardized residuals. We have residual plot, and then we have residuals, and we have normal probability plots. Everything being selected here. Okay, and the confidence interval I'm choosing for the hypothesis is 95% by default. Okay, so let's do that. Am I not getting this? C3. Okay, so the input range is C3 and this one is D3 onwards. This is where I would like to keep it. Yeah. Okay. So we get a couple of charts here. We get a couple of charts here. Okay, as you can see, there is one residual chart. Here we are giving one residual, which is variable x1, which is variable x1. And then we have the residual. So you can see some residuals being reflected. In a normal probability plot, we have tried to, take these error values. We have tried to take these error values. Sorry, not these error values. This is 5, 10, 15. It's closer to 100. I don't know, this one is slightly confusing. So let me remove this. Okay. And this is the main part wherein we can see a lot of our results. The residue, that means the predicted value of y, which we expected, was this with the equation minus 64.2. Is this the same value? 64.2. When I take an estimated value of y, I predicted for this value 64.2, 39.5, 14.8. I can take a difference between the two, which is error, which I'm calling it as minus 35.8, 34.5, 18.8, 2.1. Then I can take the standard residuals. Okay, if they are being standardized, the residuals are being standardized, I can get this. So this is my error term. This is error divided by the standard deviation. These are the percentiles, the probability outputs there. Then you can see, the intercepts. Intercepts are, if my equation right now looks like minus 88.9 plus 4.9x, so minus 88.9 plus 4.49 with standard error here, which is nothing but B1, what we are using as a denominator for our hypothesis. Then we have the t-test score, p-test, and the confidence intervals using the 95% confidence limit. We have come up with these as well. So if you want to check for the hypothesis that if intercept is relevant, or like if I say this is relevant 4.94, is it falling within the confidence interval? Yes, it is. So it is significant. Is it falling minus 88.9? Is it falling within the confidence intervals? It's not. Right? This one is, no, this is falling, sorry. This is also falling within the confidence interval. So it is also significant. So both these items are found to be significant. And that's how I can confirm. Okay, not that it would be tested in the exam. I just want to showcase it to you. Plus F test is the significance level at which they are testing is 99.7, 9.7%, which is 10 minus 100 minus 9.7 is what 92.3% confidence level at which it is conducting an F test. The F test's result is minus 5.969. Now, what you see here are the degree of freedoms. What you see here is this one is regression is this one is TSS, total sum of squares. This one is sum of squared errors, and which we are calling it as E square. And this one is the regression sum of squares, which is y hat minus y bar whole square. Okay, if we take a average of that, which we call it as mean squared error or regression, this one is an average value of it, which is 3213.9 divided by 3. This we call it as mean squared of regression, and this we call it as or mean squared error, and this we call it as mean squared regression, which is nothing but 6100.9 divided by 1. Okay, then we talked about R square. We have the R square for the model currently reflecting at 65%. The adjusted R square, leave it. Standard error of it, which is standard error of estimates, is 32.73. The observations number is 5. Okay, if you look at the same data from multi-regression perspective, all you'll have to do is within the range, select two variables. You get a chart like this. Once you get a chart like this, of course, you can create it this way and use everything. But here is the point, adjusted R square becomes more relevant here. Leave the multiple R, that is not relevant for us, but everything else looks this exactly the same. So we have all three approaches, t-test, p-value, and the confidence levels reflected for each of the intercept that is coming in. We have the residual values, predicted residual values coming in, which I can use it for forecasting. So if I have error here, I said we can take error values on one side and the predicted values on other side. Create a chart like this. I can simply, take this and create it like a chart here. Or I can, simply create it like this chart here. So this is how my error values are reflecting. On which side we have the predicted values are on the y-axis, and the squares of the errors are on the x-axis or are on the y-axis. The same chart that we discussed. So a lot of things, we have done conceptually, but when it comes to implementation, the implementation does not take as much of a time as we have taken to understand it. Once you understand this kind of Excel sheets or probably any Excel example from real life will help you break these concepts down, and they are very, very easy, to be honest. Once you start using them in real life, they're really easy. Is there any questions around it? Shelja, Geeti, do you have any questions?
No, thank you.
Right, so just wanted to make sure that you have seen some way in which these things, whatever we are studying, is getting connected in the real life, so you can correlate to it.